Okay. So, a little bit more complex circuit. And now here we have a resistor, an inductor, and a capacitor all in series. Connected to an AC source, that's supposed to be an AC source. What I'm going to do is I'm going to start with the voltage relationship in the same way that I did for an RL circuit or an RC series circuit. But what I'm going to do is combine the L and the C components, and I'm going to find a combined voltage. And then I'm going to just kind of break it down from that point. So, Vs squared is equal to Vr squared plus Vx squared. I'm just treating this as one big component, combining them. That's my starting point. So I times total impedance, square those guys, is equal to I squared times the resistance squared plus I squared times Vx squared. I'm going to cancel my i's, and so ZT squared is equal to R squared plus Vx squared, or total impedance. Same, looks like I've got this coming up with the same formula here for the other RC and RL circuits. But Vx represents the combined voltage or around those two components. Now I don't know what Vx is, but what I do know is this. Wait a second, that's not right. It's it's x squared. Yeah. I don't know how that voltage got there. Let's call that x net. So it's the net reactance. Okay? Make sure I got that right, X net, okay. Now I don't know what X net is, but what I do know is that the phase relationship of the voltage and the current across the inductor is different from the phase relationship of the voltage and current across the capacitor. So let's just look at that. I have my current reference across the inductor, and voltage leads current, so I got voltage here across the inductor. Across the capacitor, use current as my reference again, and now voltage lags current by 90 degrees. So I have that relationship. So if you ignore the current in each one of these diagrams, you can see that there is a net, that the voltage across that inductor and the voltage across the capacitor are 180 degrees out. They oppose one another. Well, here we have voltage is equal to I times XC, XL rather. Here we have voltage is equal to I times XC. So I could transform that diagram into XL here and XC down there. So X net, the net impedance of those two guys, is equal to XL minus XC, and then we always put an absolute value there because we're looking for a magnitude. You can't have negative impedance. So you're looking for a magnitude. So look what happens. If I have, now what is XL? XL is equal to 2 pi FL, and XC is equal to 1 over 2 pi FC. So the capacitive reactance is a function of the size of the capacitor plus the frequency. The inductive reactance is a function of the size of the inductor and the frequency. And typically those two guys are not equal. So the net reactance is just the algebraic difference between the two. So if XL equals 10 ohms and XC is equal to 4 ohms, so we have a 10 here, we got a 4 here, X net, or X total, is equal to 10 minus 4 is equal to 6 ohms. Okay, it's just the algebraic sum or subtraction of those two. Now, when I want to find the phase angle, what is the, if I had a phase angle meter, and we can do this on multisim, but if I put a meter across all three components, what kind of a phase angle am I going to get? I know this is going to be, the phase angle here is 90 degrees, phase angle here is 90 degrees, but what is the combined effect of all those? To do that, what I'm going to do is start out with these vectors here. Because we're looking for the phase angle between voltage and current for the overall circuit. And I'm going to, one of these is going to be bigger than the other. So there's going to be a net voltage which is going to be VL minus VC. It's going to be kind of like the absolute value of those two guys. And that is what I'm calling VX. All right, so if I have a net VX of this, and I have a net current here, my VX could be down here as well. I'm looking for that angle right there. So the tangent of theta is equal to Vx. It's the opposite over the adjacent, Vx over I. Vx over Vr, excuse me. Because we know the current and the voltage are in phase across that resistor. Which is equal to I times X net, or I times R. Those cancel. So the phase angle is this. Okay? There's your phase angle. Here's how you find X net. You just take the algebraic difference, and here's your total impedance. So there's nothing new, but there's a little bit more analysis involved. We haven't introduced any formulas that you haven't seen before. A little bit more analysis. An interesting thing happens though in these circuits. When you start adding and combining inductors with resistors, we know that the impedance or the reactance of an inductor goes by this formula. Reactance of a capacitor goes by this formula. So as you change the frequency and vary the frequency, if you have a given capacitor size and a given inductor size, as you change the frequency, the inductive reactance and capacitive reactance change. And so we're going to look at what happens when those guys are equal. What happens when these two guys are equal in a series circuit? That's a condition called series resonance. And that occurs if those two guys are equal. You have 2 pi FL is equal to 1 over 2 pi FC. When I cross multiply, I have 4 pi squared, frequency squared, LC is equal to 1. So I want to solve for frequency, and I have F squared is equal to what? 1 over 4 pi squared LC, or take the square root. Now the frequency is equal to 1 over 2 pi times the square root of LC. That's called my resonant frequency. That's when those two reactances are equal. But look what happens. The capacitive reactance, we can represent that by a vector in this direction. And we can represent, that's inductive reactance, we can represent capacitive reactance by a vector in the exact opposite direction. When those two guys are equal, these go to 0, and this is like a short circuit. The only resistance that you have in that circuit at series resonance is that resistor. So as you change the frequency in a series circuit, let's just say that's the resonant frequency, the current, this is the current, you have something like this. It's not exactly a bell curve, but basically you have that kind of a relationship where at resonant frequency, these two guys cancel, the reactances cancel, and that resistance is the only thing keeping that circuit from blowing up, because the current just spikes. Above and below resonant frequency, the current drops off. So if you ever get into a situation where you're designing and you're using resistors or inductors and capacitors, you want to be very mindful of this formula. Because if you get close to resonance and you have a small resistor, something's going to blow. Now think of it, I've been in industrial environments, so you think of, when you think of a circuit, think of you might think of a printed circuit board with, or a radio or something where you have an inductor here, and right next to it is a capacitor, and you would have that series resonance. But let's just say you were in an industrial environment, and you had a whole bunch of motors. Well, let's say your plant was 1 million square feet, and over here you had a whole bunch of motors, and over at this side, 400, 500, 600,000 1,000 feet away, you had battery chargers for fork trucks. Battery chargers for fork trucks have a lot of capacitors inside. So you have your motors and your capacitors. They're in an industrial environment that's, maybe they're spread apart by 1,000 feet. Well, think, how fast does electricity travel? You know, it's not quite the speed of light, but it's pretty doggone close. So you could have series resonance if you had just the right number of motors turning on and just the right number of battery chargers kicking on and off or whatever at certain times, at random times during the day or week or month. You could have series resonance between those two components in your plant, and everything in between represents this resistance. And if you don't have a whole lot of resistance, if it's just cables, all of a sudden you could have things start to blow up. I've had it happen. It's unbelievable. You know, at 2 o'clock in the morning, things start to burn up. Motors blow. Battery chargers kick offline. And nobody knows why. 10 minutes later, the motors that were causing resonance, they're not operating anymore. Somebody else plugged in a fork truck, and the capacitance changes, and everything's fine. A month later, things start blowing up on you. It's random. It's crazy. Even though those two components, the inductance and capacitance, are so far apart, you could still have a situation where you have series resonance. And I learned the hard way that whenever anything like that happened, the first thing I would do is get a wiring diagram for the entire facility, the electrical schematic. We call it the single line diagram for the entire facility. And I'd start looking for big motors and big capacitors in some equipment to see what the chances are that we had a situation where we had series resonance. Okay? So that's that. If I were to represent this curve in terms of impedance, my impedance curve would be, just the opposite. It would be something like this. See where that's total impedance, because when you hit resonance, these guys drop out, and the only impedance is that resistor. So it's very low impedance at resonance. You can represent it two ways. Who has questions? Again, the only formula that's different that well, a couple things. This guy here, that's new. You've seen these guys before. This is a new formula for you that's in the book. You want to know that. Make sure you know that. Other than that, there's really not that much new. If I were to have a much more complex circuit, multiple branches, multiple capacitors, multiple inductors, different multiple loops, I would approach the analysis of that circuit in the same way. I'd break it down analyzing either the voltage or the current, one after the other repeatedly, till I got the circuit to the point where it could be represented by a net impedance and a net resistance. So if I had 10 capacitors and 5 inductors, all different, connected in all different ways, there are analysis techniques to break that down, so you just have one R and one Z, one net total impedance. Once you have that, you just start unraveling your circuit little by little, and you end up being able to analyze the entire circuit, voltage and current and impedance and phase angle at every step. It's just a more complicated version of what we've done here. But this is the first step. Okay, let's do a worksheet. So I'm asking you for total impedance and phase angle for that series circuit. You know, here's your starting point. Find your reactances first. One for the capacitor, one for the inductor. Subtract the two, and then start there. Okay? That's the step-by-step approach. Okay, let's look at this. So I have a series circuit, and what I want to do is find the total impedance. So the first thing we're going to do is find our capacitive reactance and inductive reactance. Inductive reactance is 2 pi times 10 cubed, that's my frequency, times 150 millihenries. So that guy and that guy cancel, and I end up with what? I get 942 approximately. That about right? 942? XC is 1 over 2 pi FC, which is and when I work through that, I get 730.27. Good? Not good?
I got like 212 for XC and XNet was 730.
Yeah, same.
XT, you get what?
XC was like 212.
Oh, yeah, I'm reading the wrong line here. 212 for XC is correct. And XT is 730.27, right? So it'd be this minus this. Okay, so the total impedance is now 1,000 squared plus 730.27 squared. And that leaves a total impedance of, what'd you say, Matt? Oh, you did, 1238?
Total was like 1730.
Can't see. I swear I cannot see it back on. You got 1738?
1730.3. I think I did it correctly.
Is that right? 1,000? And this is this what everybody's getting?
Yeah.
I got 1238.
I did too.
1238?
Yeah.
Got it?
I left out the squares or something.
1238. Actually, 1238.26. That's almost. Okay, so that's my total impedance. And my phase angle is XT over R. So that would be 730.27 over 1,000, which is equal to 0.73027. And for theta, I'm getting 30-some degrees, 36.13. Get it? Okay, so if you could measure the phase angle across all three components, that's what you get between voltage and current. Just for fun, what's the resonant frequency of that? What do we get? I didn't calculate it. Stop here. Wow, get a crazy answer. Did you get like 0.47 cycles? What'd you get?
I got 474.
474?
That's high as well.
I missed something somewhere. I'm still getting 0.74. Which is not much. Okay. 0.74, 474, who cares, right? What'd you get?
474.
Did you? Okay, I messed up somewhere.
The formula is the 1/2 pi times the square root of LC.
Yeah, it's 2 pi times the square root of LC, and then the whole thing is the reciprocal. Okay? So let's do, before we get into parallel stuff, let's do a little multi-sim exercise where you can actually see on the computer the voltage and current and all that good stuff, phase relationships. And then we'll get into parallel circuits. And that will, you have multi-sim on there? Got it? Now, while you're doing that, in case you didn't know this, next week is the final, okay? Do I have to remind you? You should know that. So, does everybody have a file card? Does anybody need a file card? You need a file card. I want to give you that tonight. So you can have a go at it and be ready next week. I don't have any homework tonight. And I'm going to post a study guide as well for you to just review the topics. And I think what I'll do, since you had a substitute teacher last week, and I did not have a video, I think I'll just post my lecture notes for this particular topic, RL circuits, and then that's about the best I'm gonna do on that one. For those of you who were here late, I did get chosen for federal grand jury, so I'm on the jury. It's 18 months. Russell, you already knew that. You didn't know that?
18 months?
Yeah, 18 months. That's once a month, for 18 months. Every Tuesday, fourth Tuesday.